already figured out the issues of the Viato on the desktop. If you want to try it, they were able to see Arctic 7 chips at when you create the new project. Let me know if that works. So this FPGA example interface with LCD display.
So this is the LCD driver being implemented on this basis rare FPGA, and you can see that by default the basis rare FPGA is outputting hello to the LCD driver.
And you can look at the connections. So you'll need a 5 volts power supply because the LCD requires a 5 volts power supply. And this module is going to provide you that 5 volts. And a lot of students already, if you're working in my microcontroller, you know how to use this module, but many of them in the class, so I'm going to show you how to use it. So if you look at this module, it has you see plus minus. So these are the outputs of the module. Okay, and you have a jumping header here, and you can select which voltage you want to output to the plus and minus ports. So you have a jumping cable being inserted in here, so I'm selecting 5 volts to it. Okay, so you are going to have 5 volts as these two ports. They are same voltages levels, both 5 volts, but you can also change this one to, for example, jump it to 3.3 volts, and then you are getting 3.3 volts here. So you can separate these two voltage levels. This is 5 volts, this is 3.3 volts on the two rails of the breadboard. Okay, and because this is the one PCB module, do you think they are sharing the same ground or no? So for the ones you know, don't answer that. But for the ones who have never been in my control class, do you think are they sharing the same ground for these two voltages? If I'm picking up 5 volts and 3.3 volts for the two ports, do they share the same ground? And why? Or why not? So, or I want to, what I want to ask is, so for example, I power this up, okay? And I have 5 volts here and 3.3 volts here. So the minus port, the minus pin, if I have a continuity checking multimeter to check, if I have the two, it has one ground, yes. Okay, cool. And this is an adapter. And if you look at the adapter's voltage readings, what's the voltage output? 9 volts DC voltage, right? And 650 milliamps for the current reading. So anything higher than requires higher current than this one, you shouldn't use it for that device. And you plug in that jet header into this port. So plug in this one to the outlet, 110 volts AC. Okay, that's going to deliver a what kind of voltage to here? Yeah, DC. What's the voltage? 9 volts DC, right? Okay, so 9 volts DC, but it's not 5 volts. How do we get the 5 volts? Yeah, so it has a little device here. You see these two chips. So one chip is a 5 volts voltage regulator, another one is 3.3 volts voltage regulator. So there's a certain circuit which is, including the capacitors to stabilize the voltage as a filter, low pass filter. And but eventually these two chips will convert the 9 volts into 5 volts and 3.3 volts and deliver these voltages to these ports. Okay, and then if you plug in these two ports, these pins into the breadboard, it's going to deliver these 5 volts or 3.3 volts to the power rails on the breadboard. So that's how you can power up your breadboard using this module. Very simple. And then since you have power supply on the breadboard, if you plug in this one to the breadboard as well, you'll be able to wire them up. I can look at the pin outs here, the reading from D0 to D7. These are data, the data pins, 8-bit data pins. I have a read and write, reset, V out, this is I think the backlight pin, intensity pin. And oh no, sorry, A and K is a backlight intensity pin. One is the plus, one is the minus, just powering up the LED on the backlight. So VL is brightness or contrast of the display. Okay, VS is ground, VG is 5 volts. So this is the 5 volt module. I have to supply 5 volts to it. So that's why I have to use the power supply module I just showed you, right? And the voltage, the power supply for the basic 3 board is what kind of voltage? Do you know the power supply? What's the power supply voltage for the basic 3 board? For the chip, let's say for the chip, for the logic. So it's running digital logic on the board, right? It's a digital device. So what's a voltage or power supply? So it's actually a 3.3 volts device. Even though you are powering up this guy with a USB. Another question for people didn't take my controller. So what's the voltage for USB? What's the power supply voltage for USB? Is that just the one voltage, or you have all different kinds of voltage power supply voltage for USB? It's just 5 volts. Keep in mind, USB 5 volts. USB is always 5 volts, and so you power up the board with a 5 volts USB cable, right? You don't have any other power supply to it. You just plug into the USB cable to the USB port of the computer, then it powers up everything because the USB cable delivers 5 volts to the board, and you have voltage regulator on the board as well, converted to 3.3 volts as a power supply for the chip. So this chip or this board is a 3.3 volts device. However, you have to communicate with the LCD module, which is the 5 volts device, right? How that is going to work? Because all the logic levels, the logic 1 for the basic 3 board is 3.3 volts. Okay, but your LCD module is also a digital device. It has a little core on it, pretty cheap core on it, but it's a 5 volts logic. So my question is, how do they communicate? So the basic 3 board treats 3.3 volts as logic 1, but the LCD treats 5 volts as logic 1. Do they have the same voltage level for the ground? Yes. So do you connect the ground of the LCD module to the basic 3 board? Yes. Keep in mind, a lot of people didn't do that last year, so they saw issues. Keep in mind, so you see the power module, the basic 3 board, the LCD, they all have a ground pin, and that ground pin should be a common ground for all of them. You should ground all the ground pins the same node. So what about the power? What about the logic? Basic 3 board is sending out 3.3 volts as logic 1, but LCD is expecting 5 volts as logic 1. So is LCD a receiver or transmitter? Receiver is receiving data from the basic 3 board, right? So it's a 5 volts logic, which means the transistors in there can handle anywhere from 0 to 5 volts, even higher, but we don't know. But 0 to 5 volts is safe. It's a 5 volts logic. So 3.3 volts, when 3.3 volts a pulse or digital signal comes in, it's higher than 2.5 volts, usually the threshold voltage for logic 1. So whenever it's higher than 2.5, it's actually pretty well beyond 2.5. It's 3.3. So in that case, it's actually higher than the threshold voltage. It's going to trigger the toggling of the digital circuits in there. So it's actually being treated as a logic 1. So if you have a 3.3 volts pulse, it will receive a logic 1, it will receive a 1 to the LCD. However, for example, if the LCD is writing to basic 3, is there going to be an issue or not? It could, right? So the LCD does have a writing function in it. I've never writing anything from the LCD to a different device, but it does write out, or you can read from LCD using a microcontroller. But just in case, we assume that LCD is going to write to an external device, to basis 3. Is that going to be safe or not? Is it safe to write from LCD to basis 3? Yeah, because if you're writing out a signal, so sending out 5 volts at logic 1, but basis 3 is probably not able to handle 5 volts as a logic signal, the digital signal. So the question is, why you are able to handle 5 volts power supply from the USB, but not the 5 volt signal? No, I'm asking why your basis 3 board can handle a 5 volts power supply from the USB, right? So that's the 5 volts USB power supply. You do have a 5 volts on the board. Why it is able to handle that, but not able to handle 5 volt signal from the LCD or anything else? Stepping down the power supply, but okay, so the 5 volts power supply is connected to the regulator, which is able to handle 5 volts and step it down to certain servos as power supply for the chip, which is this guy. Okay. However, the digital signals are connected to it's not GPL, but digital pins of the chip. It's directly connecting the transistors, the devices in the chip. But the devices are certain servos devices. Okay, 5 volts is gonna probably burn it. Okay, so it's gonna damage the transistors in the chip. So that's why if you are writing back, usually what you have to do is use a voltage divider to step down 5 volts to certain servos, or there are some level shifters that can use. It's important to know because for the project, we are going to use a joystick, which is the 5 volts device, but to use a level shifter in between the Arduino and the basis 3 board. So another question here for a lot of people is why we don't just have a standard voltage power supply, for example, 5 volts for everything? Why do we need sometimes we need a 3.3 volts and 1.8 volts sometimes? Why do we bother? Lower power usage, right? So it's a lower power consumption. But another thing you need to know is whenever you make the size of the transistor smaller, they are not able to handle high voltages. Usually, it's the highest voltage you can handle is like 1.8 volts. You want to make the transistor smaller because you can integrate more transistors in the same footprint of the chip. So the trade-offs. Okay, so these are the pin outs, or the name of the pins of the LCD module. Okay, and these are the functionality of the pins. So if you look at the connection here, it's a lot of wires. So where can you find the connection schematic of the circuit board here, of the circuits here? I don't have a schematic for you guys, but there is a description in the PDF. You just simply click. Okay. So the code for the first example is provided. So that's a driver, LCD driver. And the second piece of code is translator module, the top module. However, the top module being used in the textbook is based off a different device. So I've never seen that, so I don't know what the device looks like. But we are going to connect the pins to different ports. So what's going to happen is the top module receives signal from the switch. So if you turn on a switch, show the video.
So this is the LCD driver being implemented on this basis FPGA. And you can see that by default, the basis FPGA is outputting hello to the LCD driver. And I have different switches. Just gonna send a different character text to the LCD.
Show different text on it.
Talk.
Right.
And
it's all based on
switch
the whatever you put in.
It's gonna output college.
Lookup table.
And
in the code.
3 is sending out Durango.
Switch,
and then USA,
then shows a
then
certain
Colorado,
on the LCD module.
And finally,
so that one is controlled by the top module because the switch is being shorted to a certain GPIO pins or digital pins on the board. Oh, I have to go back again one more time. Sorry. So if you look at the GPLs, are these guys, these headers. So you can see on the top right corner, these are the JB pins, JC pins, it's just the digital pins of the chip. JA and JXAC pins. So you have to look at your constraint file. See if you do have these statement over there, and have to uncomment the J pins in the constraint file. Don't forget to do that, otherwise it's not going to compile. And if you look at the layout, I think this one usually is a little marker here. It should be the first pin, if I'm right. So what's going to happen is JA is here on the right? So JA1 and JA7 is over here. Based on that kind of order, you can find out all the other pins. So these two are both power pins, and these two are both ground pins. You just use one of them. They're all shorted together on the board. And you got all the other JA pins and JB pins as well are here. So based on the description over here, it just tells you everything about the connection. So you don't have to worry about that. Just to read through this paragraph. So the LCD's 8-bit data bus line DB0 to DB7 should be connected to JA port of the board. So it's JA0 to JA7. So the DBs are here. See DB, the data 0 to data 7. Okay. You can see all the other connections are all covered in this paragraph. And the potentiometer to adjust the contrast of the display. Okay, so that's the potentiometer. If you haven't used this potentiometer before, I'm going to show you how to use it. Okay, so that's the middle pin of the potentiometer, and these are the two terminals of the resistor. It's a 10K potentiometer, so which means the resistance in between these two terminals, and that's the middle terminal, that's the output. So what you want to do is connect either one, doesn't matter. So one of them to ground, one of them to power supply. Okay, 5 volts because it's connected to the LCD, so it's going to be 5 volts and ground. So the middle pin will be the output. So the middle pin is the output, should be shorted to VO. VO here. Okay, so you can adjust the contrast of the display. So it says the easy VR shield, we don't have it. So we are using a switch, not a switch, but several switches to give a signal to the basis board in order to display a certain character or text on the LCD display. So now let's get into the Verilog here real quick. So it has a counter, so it has two modules. One module is the driver, one module is a top module. So the driver has a data input pin. It's trying to receive the data input from the switch and then send it out to the IPGA. So I'm going to have several questions regarding the wait time for this counter for both the driver module and the top module. So they have a different count max for these two modules, and you should look through this Verilog code and tell me why they have a different rate on the quiz. So the initial begin can be compiled or can be synthesized on the hardware actually, but the initial begin will be only executed for once. So whenever you part it up, it's going to be executed once to give the initial values, and then it won't come back again because it's not being triggered and updated by the clock, right? So it's just after you part it up, it's being initialized, and that's it. It's not a loop, it's a hardware, it's not C++. But however, all these following ones will be updated because you have a clock. Okay, so whenever the clock negative edge is arriving, it's going to do all the updates over here instead of a loop, as what you did in C++ or Python. Okay, and it's switching in between all the states in here. So the init states will do all the initialization for the LCD. So for example, it set up the resolution of the little unit, display unit, and clear it the display. Whatever residues you have on the display is going to be cleared up, and some other configurations you want to follow. So it's going to run through all these initialization in this state, the init state, and then it's going to wait here whenever the enable pin, the writing enable is being set. Then it's going to run the write state over here. So the write state is very simple, just receiving data from the data import and then throw it to the data out. That's it. Just grabbing it from data in and throw it to the data out. All right. That's it. No more code description. People are getting sleepy. I'll let you guys do it, okay? And that's the LCD. And then we come back to the USB. I'll just tell you the requirements for it. Okay. So the USB module on the IPGA board requires a little chip to communicate with the computer or communicate with the keyboard. So that chip is called a UID, USB HID port. So that's a microcontroller from PIC, which is a microchip microcontroller. Has been super popular in the past many years, but recently Arduinos are dominating, but this was super popular before. So this is a microcontroller in between the USB and the FPGA. It's converting the USB to serial and serial to USB. And there are only two modules for this example. So what you need to know is for the keyboard, whenever we design the hardware as a driver to operate the keyboard, it's a different device as a push button or switch. And you have to think about why the keyboard is so different. A push button is just the one finger, you keep pushing it, right? But why the keyboard is different? So what we are doing here is trying to figure that out because we have to put two hands on the keyboard and we have to type really fast, right? So a lot of times you have two keys being pressed at the same time. So which key should be, put into the monitor, right? So CPU. So that's all the reasons that we need a certain protocol for the keyboard. So when you press it, it shows a key code. So the key code is a ASCII code here. Okay, from the keyboard. Every key has a key code. And it's going to keep giving you the key code until you release it. If you release it, it's going to give you F0 and followed by the key code again. So F0 will be an indicator telling you that now the key is released. And right after that, it's going to do all the following and get into and put the key code into the CPU. Otherwise, just keep waiting there. Okay. And there are several things, including the parity bit checking, and is embedded into the keyboard. So I have a question on the quiz asking you if it's an odd or even parity checker or indicator. And so today in the class, we are not going to, you guys are not trying to demonstrate it, right? Just finish the quiz. So go through the code. I'll be here if you have any questions you can ask. So the second task is a serial communicator, which is a transmitter to be included into the USB module. So I have a keyboard, you type something on the keyboard, and the IPGA receive it and send it to the serial monitor on the computer. So I have to put your UART module in here. I have a diagram shows all the wires and connections. And here's a demonstration. Okay. So these are the tasks for this and next week. Do you have any questions on anything? So this is due next Thursday. Lab is due next Wednesday. Quiz is due today after class. Hope we can finish it in class. Okay. Oh yeah, I will. Yeah, I'll start working on that next week.